Earlier we have seen the time dimension and the frequency dimension. In the time dimension, we have seen slow fading, fast fading, and then at the frequency dimension, we have seen flat fading and the frequency selective fading. Now in this video, we are going to talk about spatial characteristics. Now let us start our discussion. Let's say we have an antenna and at time delta t, this antenna has moved a distance of delta x and now is at the new location. And delta x is equal to velocity into delta t. We also know that v upon c into fc is equal to fm. From here we can substitute the expression of velocity to this expression. What we get is delta x is equal to fm upon fc into c to delta t. Now if we just obtain this fm into delta t from here, fm into delta t is equal to delta x into fc upon c, and we know that this fc upon c is nothing but 1 by lambda. So as a result, what we get is we get fm into delta t is equal to delta x upon lambda, and we will see how this expression is useful. So from flat fading under the isotropic scattering, that means p of theta is equal to 1 over 2 pi. That is, at the receiver, all the rays that are coming to the receiver, they are coming from all the directions and with equal probabilities. So in this case, we have achieved the expression of correlation of the channel with itself, which is the function of omega p, that is the signal power divided by 2 into j naught. J naught is the zeroth order Bessel function of first kind, and 2 pi fm delta t. If we substitute this expression of fm into delta t in this expression, we are left with the correlation as a function of delta x and lambda. And similarly, we can also obtain the correlation of envelope of the received signal with itself. Here, alpha is equal to mod of h of t. And we can also see that this correlation is also a function of delta x and lambda. Now, under this condition of isotropic scattering, that is p theta is equal to 1 by 2 pi, if we have a spacing of 0.38 lambda, that means if delta x is equal to 0.38 lambda, this correlation is equal to 0. So what we can say that at delta x is equal to 0.38 lambda, when we have two antennas and the spacing between the two antennas is 0.38 lambda, we achieve uncorrelated signal at both these points. And this is very useful when we study the spatial characteristics. So now, in case of time dimension, we have studied Doppler spread. Then in case of frequency, we have studied delay spread. Now in the space dimension, we will study angle spread. The Doppler spread means the frequency is now fc plus minus fd comma n. That means we have a spread in frequency. The received signal is now having a frequency of fc plus fm and fc minus fm. That means we have a spread in frequency, and since this is due to the Doppler frequency, we call it Doppler spread. Then the delay spread means when an impulse is launched, what we receive, let's say this is the delay axis, what we receive is the echoes that are coming at different delays. So as a result, the impulse is now delayed in time. So with the angle spread, what we mean is that, let's say we have a base station and we have a receiver. So in case of rich scattering environment, we have multiple scatterers around the mobiles, or we may have some trees, and the signal transmitted will be received by the mobile from all the directions. So as a result, what end up at the receiver at the mobile is the spread of angle of arrival of the multipath component. And this is what we call as angle spread. The spread in the angle of arrival of the multipath component. And since here the spread is coming from all the directions, so that means we have huge spread. If the components they are coming from some direction, the spread would be less. Now let us define this. If psi a theta is the average power as the function of angle of arrival, that means average power in the theta component, then theta RMS can be defined by this formula, where theta bar is the mean angle of arrival, and this is the normalization of the power. And this theta RMS, it causes the space selective fading. And for this we usually define coherence distance. So we have also defined earlier for the time dimension, we defined coherence time. For the frequency, we defined coherence bandwidth. And now for the space, we will define coherence distance. And we have seen that in case of time, it is inversely proportional to the spread in frequency. For the coherence bandwidth, it is inversely proportional to the delay spread. And now for the coherence distance, we will see that when the spread is more, that means we have a very less coherence distance. And similar to the time and frequency, again, this coherence distance is inversely proportional to the theta RMS. So now we have seen that in case of time and frequency, we want coherence time and coherence bandwidth to be as higher as possible. Of course, there are some demerits of that, but we usually love to have this high value of coherence time and coherence bandwidth. But in case of coherence distance, we want this coherence distance to be as smaller as possible. And why? Because if the coherence distance is smaller, that means if this is, let's say, if this is 2 points, this is 1 point and this is 2 point, and the distance between them is coherence distance. If this distance is greater than this, then we can say these 2 points are uncorrelated. Because of this property, we can have multiple antennas that are closer to each other. And this is only possible if we have a very small coherence distance. That means if we have a mobile that is of 5.1 or 6.1 inch and the coherence distance is very small because it is a rich scattering environment, so we can place two antennas that are very close to each other inside the mobile receiver. But however, in case of base stations, the two antennas are sufficient far apart from each other compared to the mobile, because we are not have much scatterers around the base station. So in case of mobile, we saw that coherence distance is smaller because the angle spread is more. More the angle spread, less is the coherence distance. Whereas in case of base station, the coherence distance is larger. And how this is beneficial, we have studied this, because lesser the coherence distance, we can have two antennas closely packed to each other. Okay. So what we need to understand is, so this is the diagram which has earlier been studied. This is the transmitter and we have receiver. So we say this is the flat fading scenario when we have only one ellipse, and we have multiple paths coming from the scatterers that lie on this ellipse, and we have this tau 1 and all the propagation delay of all the taus, they are equal. And now when we have multiple ellipse, then we have multiple propagation delays. So what we need to keep in mind is this h should always be a function of tau as a delay axis because of multiple ellipses, then function of time, and then theta because at the receiver it can come from different directions. We don't know with which angle of arrival it comes at the receiver. This is theta. So always when we talk about channel conditions, we describe the h in terms of delay, time, and theta.